Yeah. Okay, so let's start with the last part. Shouldn't take an hour. There's not that many technical slides on this last part here. So this is about privacy. And we talked a bit about privacy before. Actually, before I start, I want to give you a few anecdotes. I talked to a few people over the break, and then I remember all these anecdotes of actually doing linkage over the last 10 years or so, and what we found out and when we developed and tested our algorithms. So the first funny case was in the early 2000s, right at the beginning, where I was down to look and develop record linkage techniques. We had access to a New South Wales midwives data set, so basically 1 million records of all the women who gave birth over a 10-year period in Sydney and surrounding areas. So the task was to kind of link to a longitudinal linkage. So we developed our linkage techniques and ran the code, and then we found 4 women who, according to our algorithm, had 4 births within a 12-month period of time. So okay, well that's okay. There must be a bug somewhere in our program. So we went back and tested and everything, and we got the same results. So we sent our these cases back to the New South Wales Department of Health and said, "Hey, can you please double check what's going on here?" Okay, guess what was the case? Was it our programs? Any guesses? Sorry? Yeah, that's correct. We had another case. What else? No, it had to do with birth. So we had a triplet, and less than 12 months later on, the same woman gave birth to a single baby. Right. So that was validated. So we knew, okay, our algorithm works. That's great, right? So another case is Maurice. Sorry. No, good.
I just said lucky her.
Yeah, I don't know. So, what is the kind of strange things you identify when you do linkage, right? Another more recent case is there's actually one database which is semi-publicly available. It's the North Carolina voter database. So in America, the different states have different ways of how they publish voter registration information. North Carolina has its database on a FTP server, and the URL is published in a certain computer science papers. So anyway, I've been downloading this database for the last 3 years on a regular basis to basically build a temporal database, and because we know supposedly everybody has a registration number, a voter registration number, and we thought, hey, that must be fantastic, that's clean, that's the truth, right? Well, if you think that the American election is very tight with regard to a few hundred votes, I can tell you this database is totally messy. There's 50 people who share one voter registration number. There's people who have up to 10 voter registration numbers. It's a complete mess. And it has to do that it's still paper-based, so if somebody moves around, they fill in a paper form which is being sent somewhere. Somebody types that thing in, then it's being collected. Anyway, so we've developed linkage techniques to look at temporal aspects of when people move and change their names. And then I found this case of 4 people, same first name, same middle name, same last name, same address, different dates of birth. Right, okay, everything the same except different dates of birth. That's not, okay, what's the problem here? So I typed in the name to Google, as you do, and I found this website of death notices. And there was one death notice where it says something like, okay, I make up the name, John Leonard Smith, the elder, died. His son, John Leonard Smith III, his grandson, John Leonard Smith II, and his grandson, John Leonard Smith Jr., and things like that. So again, this is about these, I talked with some people over the break, these special cases, 1 in 10 million, right? 4 generations of the same family, same first, same middle, same last name, and they all live together. I don't want to go to North Carolina, right? So, but these things are happening, right? Graham, you told me the one from Tasmania. John Bass told you, right, the one about the twins. It's like, right, so there's apparently a case in Tasmania, at the southern end of Australia. We've been there, beautiful island. The people don't travel a lot. It's not being recorded, this, oops. There's apparently a case where there are twins, and on the date, on the birth certificates, there are different fathers. And that's apparently validated to the people who've done the linkage, right? So these are the cases where they occur once in hopefully 100 million or so, But these are the cases which I think you're never ever going to get correct unless you actually go and talk to the people. And maybe you don't want to go to Tasmania and talk to these people. I don't know, right? But again, the issue here is that, as I mentioned before, we will have records which are exactly the same. They're about different people. We will have records which are completely different. Again, the example of celebrities, which we have in our credit database, where they have an alias in one record, different address. The date of birth is the only thing which is in common. They're the same people, right? Without domain knowledge and being able to talk to people, you never get that correct. However clever your techniques are, you never get these things correct, right? And I'm sure there's different, everybody has their anecdotes if they do linkage, right? Okay, so let's move on and talk about privacy for the last hour or so, maybe less, right? So when we link, sometimes we want to link in such a way that we cannot identify the people which we are linked together. We're only interested in what we call payload data to do our health, social science research, or whatever there is, right? So we might not be interested if the person's called John Smith or Mary Miller. We only need to know their age, group, their gender, their postcode area, and things like that. But we need names and addresses to do the linkage. So we can't do this without encrypting data, because once we encrypt data, as I show later on, we're going to lose the details of names and addresses. So basically what we want to do is something like we want to link databases across organizations such that, again, this could be different hospitals, a health department in a hospital, different government agencies or private and public service organizations, in such a way that none of this sensitive information, names, addresses, etc., ever has to be exchanged. So information doesn't have to be revealed to anybody else and cannot be attacked by anybody else outside of an organization. So that's what we call privacy-preserving record linkage. I'll show you basic techniques a bit later on. The big challenge here is that we can't simply do encryption, because encryption means if you have different values, the corresponding code will be different as well. So Smith or Peter and Pete will have different codes. You can't do string matching again, approximate matching. Once we move into that area of security and privacy, we're going to talk to cryptographers, and for them, either you can prove it's 100% correct and secure. If it has the smallest flaw, you're out. For us, it means the paper doesn't get published, or techniques are not going to be accepted. So we basically have to prove that a technique cannot be attacked. And there's many different types of attacks on secure computer systems. I'm going to show you one example, a frequency attack. And because all this cryptographic encoding and encryption has high computational overheads, we can do it at the moment, but again, it doesn't scale up, right? Because the computational overhead might be 100, 10,000 times or even more, compared to simply calculating things unencoded. So let's have an example. And again, if you're a demographer, I'm really sorry if I get it completely wrong. It's a made-up example. So let's assume we have a demographer, and she wants to investigate mortgage stress, or people who buy a house and get a huge loan from the bank, which I'm sure is an issue here. It's a big issue in Australia. How does this affect people's mental and physical health? I'm sure it does, right? If you got this $500,000 loan on your bank and you're worried about your job and your kids' education and things like that. To do such a study, the demographer could either go out and recruit 100 or 500 or 1,000 people and talk to them, or she could try to do this population informatics approach. Try to get all the information she needs for such a study, which basically means she would have to go to the government to get information about social security of people, health, so doctors, hospitals, education, potentially data from the police, who knows, right? Lots of different sources. She would also have to go to the private sector to get information from health insurances, of course the banks, to actually to see who has what kind of loan and what the conditions are, etc. And you can't do that. At least in Australia you can't, I'm sure you can't. You can just walk down to the government and say, hey, look, I'm this fantastic researcher, do lots of good stuff, can I get your data, can I get your data, can I get your data, etc. That's just, you can't go to the police ask for the data, right? So, okay, so we basically can't do this at the moment because of legal aspects, of commercial aspects. of privacy aspect. If the, I don't know what the public would think if you propose such research and publish this and say, that's what I want to do. I don't think there would be a high support for this. But again, coming back to what does the researcher actually need? She doesn't need to know if John Smith and Mary Miller have a mortgage and they have 3 kids and he's unemployed, etc. They need to know the characteristics. It's somebody living in that postcode, age between 25 and 35, they have 3 children, etc. But we need the names and the addresses to do the linkage because we don't have the identifiers, right? So that's the challenge we have. Can we do this kind of research? Or this kind of linkage? So the health domain has done quite a lot of work in this, especially in Australia in the last 15 years or so. Australia actually had one of the most advanced health linkage centres initially in Perth, and now in most states we have data linkage centres which work in the health domain. And the idea is that we link data together from different health sources so we can do public health research, analysing what kind of diseases people have, etc. Again, data comes from the health system, from, at least in Australia, we have government-funded Medicare and things like that, pharmaceutical benefit schemes, public-private hospitals, etc. So the idea of this best practice approach, which was developed in the early 2000s, is that we split the identifying information from the medical information, so that they're clearly separated. The identifying data, names, addresses, dates of birth, which we need to do the linkage, are given to a trusted linkage organization. I'll show an example on the next slide. They never see any of the medical information. So that's kind of a separation of the sensitive information and just the names and the addresses, right? They do the linkage, and back comes an encrypted identifier, which basically tells record X in one database is linked to record Y in the other database through number 45, but nothing else. Then this information is given to the sources, which can attach the payload, so kind of the medical information, which is agreed upon by an ethics approval by a university, and that's then given to a researcher. So the good thing with that is that the linkage unit never sees the payload data. The researchers don't see the personal details, so kind of say, well, it's all good. Communication is encrypted. Right? So I think that's pretty secure, right? So here's an example of, again, linking that to the previous demographic research example. So we have 3 steps. We have the mortgage database, the mental health database, and the education database. We have names, addresses, you identify information in all 3. Here we have financial details, health, and education details. In the first step, the 3 data sources send the identifying information, the blue path, to the linkage unit. Encrypted, but the linkage unit decrypts it and has access to the real names and addresses to do the linkage. This is traditional linkage as we discussed the last 3 hours. Okay, so the linkage unit does probabilistic validity and Sandro, whatever there is, links records together, assigns every linked record pair a unique number, randomly chosen but unique, and sends these numbers back to the data sources. So it basically says, your record 5 gets identification 42. Your record 7 gets identification 42. So 42 links these 2 records. The identifiers are back with the data sources. They attach the payload data and then send that random identifier to the researcher, which now gets basically a record with 42 attached, a record with 42 attached, and a record with 42 attached, and it can link these together. So the researcher never knows what who actually 42 is, but she gets all the information she needs to do her research. That sounds pretty good, right? It's kind of a separation of the linkage and the sensitive payload information. And that's the paper done here from actually John Bassey's the guy with the Tasmanian example. So that looks good, right? But the problem here still is that the linkage unit gets all the information. It has to decrypt the names and the addresses. Basically, it's a large database of names and addresses of people. So the linkage is done unencrypted on the original data. metadata about where the data comes from might still reveal some information, right? If you know that this database is from a cancer registry, then you know that the people in there will have cancer, right? Things like that. So there's some information which has to be kept. So it's not completely secure. There's also the possibility of collusion and of internal attacks. So collusion is if several parties work together to try to identify information from another party, which maybe is not a big issue in a government environment, but in a commercial environment, it's a big issue, right? There's two companies work together, exchange secret information so they can identify what the third party has. Insider attack is a much bigger problem, as we know from Edward Snowden, right? He had access as a system administrator to all the NSA data. Somebody in these linkage units has access to all the data. If they want to, they could go away and sell that information. Or it could be somebody makes a mistake in the encoding and the encryption of these systems, these servers, and somebody hacks into those and gets access to all names and addresses of everybody who's ever been involved in a linkage, right? So, while good and it works in practice, so this is being done in Australia for the last 10 years or so, it has vulnerabilities. And what we're trying to do with privacy-preserving record linkage, we want to do it in a provable, secure way. That we can prove that nobody can get access to any sensitive information, sensitive names and addresses. The way we do this, we encode the data at the data source, and I'll give you an example on the next slide, I think, about how we could do this. I'm not going to go into the technical details. At the end of the process, we only reveal information about the matched records. So again, as similar as what happens in this scenario here, we give unique identifiers to the matched records, which are then given to the researcher. And we can make sure we can prove that our algorithms are secure against different types of attacks. This is very challenging. This is a fairly new research area. It's maybe started 10 years ago or so. And we are far away from practical systems. But once implemented, they can completely change the way we do data analysis and linking across parties. And one thing I have to mention is the linkage, the privacy-preserving linkage, prevents any sensitive data to be revealed during the linkage phase. It doesn't prevent sensitive data to be published. So once we've linked records together, and again we attach the payload, some of these medical details, that information can still be leaked or being revealed, right? So there's a different type of research which is called privacy-preserving data publishing, which is also computer science statistical agencies working on this. How can we prove that we can reveal information to the public at the lowest possible level such that we can make sure nobody can re-identify an individual from the published data? And that's hugely challenging, right? Because all the data which is out there, there might be, it's like a jigsaw puzzle. You could reveal some data and you checked everything and nobody has the same. There's always like 10 people with the same characteristics, but there might be some additional information which allows somebody to do a re-identification. So again, this is ongoing research, but of high interest to national census agencies. So here's a picture from before about the record linkage process. And basically everything in that yellow box can only work on encoded data. Right. So encoded data is different from encrypted data. You encrypt data with a key, like a password, and you can decrypt data, or another party can decrypt data and they get access to the original value. The aim of encoded data is, again, you convert the data into some different representation, but you cannot go back to the original one. I'll show an example next. That's the whole point, right? We encode the data here such that everything which happens in here has to work on the encoded data. Even if somebody gets access to the encoded data, they have no chance to identify the people in that data. That's the whole point, right? I could basically publish that data of codes because I know I can prove nobody can identify the people in the database, right? That's actually the assumptions we make, right? In a way that, actually the assumption we make is that one party tries to identify the information from the other party. And if that's possible, then the whole thing falls apart, right? So everything we do in the yellow box has to be encoded, At the end, we want to reveal the matches. So which record matches, give them identifiers. We don't want to give any information away about the non-matches or the potential. Well, the potential matches is an open research question, so is clerical review. If everything is encoded, how can we do clerical review on codes? Doesn't really work at the moment. There's been one paper which started to look into this. So what are the basic protocols? So we have two different basic scenarios, and Alice and Bob are not people. We're using the notation which cryptographers are using, and they're using Alice, Bob, Carol, etc. for organization, for units. Could be government agencies, etc. There's two different types of protocols, and for different scenarios, we have one of these. These are the basic ones, right? So the first one is we only have two data sources. Let's say two companies. They want to identify which records do they have in common, potentially two customers, or two suppliers. Let's say you have two big supermarket companies. They want to potentially merge, but they want to see how many suppliers do we have in common. If you have a lot of common suppliers, then the merging might make sense. Actually, that's not a good example. The example, a much better one is pharmaceutical companies. Okay, let's have two pharmaceutical companies. We all know they spend billions of dollars on developing new drugs. That's highly sensitive information. That's a corporate knowledge. If they want to potentially merge, how do they do this? They're not going to grab their piece of research on the development, go into a room, lock it up and say, I'll show you mine if you show me yours thing, right? That's not going to happen. They're also not going to go through a third party, a consulting company, because there could be the issue of collusion, right? If I'm a consultant and one of the pharmaceutical companies says, hey, I give you $10 million if you give me all the sensitive information from the other company. Why wouldn't I? And go off to the Bahamas if I'm a corrupt consultant, right? So then maybe there's not corrupt consultants, okay. So we only want to have the two parties. How do they identify how much research they have in common? So maybe looking at similarities of drug names or of genome sequences, of patents, etc., without revealing to each other what they actually have. Right? We can do that. We can really basically say, yeah, we exchange this encoded information, and at the end we come up with a number which says 42, which is the percentage of what research there is in common. And the way it's being done, let me go this step here. This is more the government kind of case where we have a somewhat trusted organization, such as a government department. So Carol will be the government department, and Alice and Bob are two hospitals. They trust each other, so we can use Carol to do the linkage. But still, Carol doesn't get any names and addresses. She just gets these encoded values. All of these protocols have three basic steps. The first step is the parties have to agree upon which algorithm to use. So how do they encode the data, what attributes and fields to use, what pre-processing to use, etc. It's kind of setting up the whole system. In the second step, so you can see important is that in the three-party protocol, Alice and Bob don't tell Carol what the algorithm is they're using for the encoding, because once Carol knows that she can do some attacks. The second step is that Alice and Bob encode their data and then exchange it somehow, or send it to Carol. So Carol gets the encoded information, or Alice and Bob exchange parts of their information so they can actually do the linkage. And then the third general step is, in the two-party protocols, some information about the links is being exchanged, or in the three-party protocol, Carol tells Alice and Bob what she found in the linkage. And again, this could potentially just be a number. I found 25,000 records which have a similarity about 80%. Or it could be the identifiers of these numbers. And then Alice and Bob can potentially add the payload and send that information to the researcher. The important thing to reiterate is Carol never sees names and addresses and dates of birth, etc. She only sees encoded information. So I'll show an example soon. So here we go. That's actually one of the basic building. As I said, I'm not going to go into the different techniques given the time and all in the last part of the workshop. Hash encoding is one of the basic building blocks. So again, this is something which you use every day. If you do secure internet commerce, internet banking, you use these hash encoding functions. One of them called SHA is a Q hash algorithm, which is a standard. The idea of these algorithms is that you have a value, a string or a number, you encode it, so you replace it with another value. That's very easy. If you have the code only, it's almost impossible to identify the original value. So here's kind of what I tried to show us. So Peter is being encoded into a bit string. So this looks random, zeros and ones. It's often represented such as a character string. Going from Peter to this string here is very easy. If I give you this, and you're a clever computer scientist, and you have the biggest supercomputer in the world, you cannot get that. That's the idea, right? So one way is very easy, the way back is impossible at the moment. Right, okay, so the problem now is we can easily do exact matching. Right? I have two databases. If I use the same hash encoding, if Alice encrypts Peter, she gets this code. If Bob encrypts Peter, he gets this code. 2 times the same code, it's the same value. Right? That's straightforward. And the first such techniques were developed by health researchers in France in the mid-90s. They actually employed SoundX before, and then encoded the SoundX values. And they got pretty good results, right? That's the first time somebody showed you can do this. So the linkage is based on these random character strings. You can still identify who are the same people at a certain level. But as we know, data is dirty. So I can never link Peter and Pete. Because in average, half of the bits are going to be different. The resulting code is completely different. I can't do a string comparison on these codes. There will all be zero similarity. So how do we do this? Right? I'm not going to tell you today. It's way too complicated, and pretty tired as well, actually. I'm just going to show you one example of what of these attacks I mentioned before. So frequency attack is where someone listens into communication. This is one of the types of attacks we have to prove that our technique is not vulnerable to. In fact, if I go back, so let's say I do this for my first names, for my last names, for my postcodes, for my suburb names, etc., and I transmit all these codes. Now, Smith and Peter will be more common than more rare names, right? So this code will be more common. And that's the idea of a frequency attack. So here is a graph which shows, again, made up, of course. This is the count how often a value appears. These are values sorted according to their frequencies. So let's say the black line is the frequency of surnames, let's say from a telephone book. The dotted line here is the frequency of postcodes, also from a telephone book. And now I'm listening to the conversation or the communication between Alice and Bob. And I learned that the distribution of the hash codes is this dashed line here. Right. So what can I learn from this? Well, it's very likely that these are surnames being communicated between Alice and Bob, right? Because they have a very similar distribution of their frequencies. Based on that, I can see, well, these very frequent codes must be Smith and Miller. I don't know what's Williamson. I don't know what else is common here in Scotland. So these three, right? So now I have something to start with. Now I can basically say, well, I know there is a certain number of these encoding algorithms. I can now brute force what's called a dictionary attack. I go grab a telephone book and encode every potential value with all the known algorithms. I get a hash code, and once a hash code matches to a hash code from Alice and Bob, I've cracked the encoding. Then everything falls apart, right? So this is a frequency attack, which is again something common in cryptography. We have to prove that we cannot do this. And if you remember in the hour before, I mentioned the things about the block size is important, right? That's exactly the reason. If I can make sure that all my blocks have the same size, so and encode values in blocks, so every blocking key has the same frequency value, then basically I get a very flat line here, and the attacker can't do any frequency attack anymore. This is a simplification of things, right? This is one of the different attacks. There's much more complex attacks as well. What do I do here? Right. So I think this is actually almost the last slide here. So without going into the details, if you're interested, we've done lots of work in this area. It's still an open research area. I think it's very exciting. It's very challenging because you have to learn about cryptography and know about these techniques. I have to fight against cryptographers who don't like your papers because they work, but they're not 100% secure. So there's different techniques. I mentioned the first one, the French approach, which was developed in the mid-90s, which basically is exact matching on hash codes, and that worked, but the quality wasn't very good, right? In the early 2000s, the first techniques which basically converted the string comparison functions into privacy-preserving versions were published. So people at Purdue University in the United States, they developed a secure edit distance, such a way that if you have two strings, you can compare and calculate edit distance, if you remember from this morning, such that we only learn the final edit distance and nothing else. We developed a Q-gram-based approach, which allows us to identify similarity based on these Q-grams. Again, that was the first approach. It worked, but it computationally completely exploded. So when we did experiments with Australian surnames, instead of having to send the database once between organizations, we have to send it 70 times. Surnames are fairly short. With the long Australian Wululamu and Wollongong and all that suburb names, it increased to 7,000 times. Right? So that's not too bad, right? I mean, instead of sending 1 megabyte, you have to send 7 gigabytes. Okay, we can do this now, but still, it's not scalable, right? So the third generation, starting from the mid-2000s, 2005, 6 onwards, has looked at privacy-preserving blocking. And again, there's often a bit of a trade-off. So we might say, yeah, it's okay if we maybe leak a little bit of information about the block size, but we can do things scalable, right? That's where then you have that trade-off between linkage quality, scalability, and privacy. And getting all three, but getting privacy provable correct, or provable privacy, and scalability, and high linkage quality is an open question at the moment. It's often a trade-off which you have to do. And the last 5 years or so, there has been at least 30 different techniques. We've got a survey paper on this from a PhD student. Again, I don't want to go into the technical details. If you've heard of Bloom filters, they look very good. Again, there's all this mapping stuff, there's random things. I could talk for hours on this, but probably I shouldn't. So this is a really exciting research area. I think if we get this done and it works, we can open up a whole range of new types of analysis between organizations. It's not just a challenge with regard to the technical aspects and the algorithms. It's educating people that these things actually work and basically show them you can trust us. We're computer scientists. We can prove that that you cannot reveal any information. One of the big challenges, actually that brings me to the next slide of the, okay, one more slide. This is a nice one. Then I come to the conclusions. This is one of the building blocks which we're using. I think it shows kind of what you can do, right? There's this whole research area called secure multi-party computation. Again, started by mathematicians, cryptographers in the 80s. The idea is you have different parties, and they want to calculate a function, any function, such that everybody puts their input into the function. At the end, everybody gets the result, but nobody learns the input from the other party. Sounds like crazy, right? But here's a very simple example. Let's say I want to sum numbers across several parties. Could, for example, be hospitals and the number of disease cases, which are highly sensitive, so let's say HIV and certain types of cancer. If the government requires that information to be collected and aggregated, the individual hospitals or maybe doctors don't want to reveal that information. So we do what we call a secure summation. So we want to calculate S, which is the sum over the xi. So xi are just numbers in our different hospitals. Nobody wants to reveal the x. Everybody wants to know S. How do we do this? This is a very simple approach. We have the three parties, party 1, party 2, party 3. The first party starts, and she selects a random number, Z. Completely random. She doesn't tell Z to the other parties. It's a secret number. she adds her own x1 to Z and sends that to party 2. Right, so she adds 55 to 999. She sends 1054 to party 2. Party 2 doesn't learn anything because it doesn't know the random number, right? It just gets 1054. Party 2 adds its own number, 73, to it. That gives us 1127. And it sends that number to party 3. Again, party 3 doesn't learn anything. From 1127, it cannot learn anything about party 2's number or party 1's number because it doesn't know Z. Party 3 adds 42 to the sum and sends 1169 back to party 1. Because party 1 knows the random number, it can subtract the random number, and it learns that the sum is 170. But it doesn't know the contribution of parties 2 and party 3. So party 1 learns the sum, and now it can send the sum to the others.
It knows the sum of party 2 and party 3.
It learns a little bit about this. That's what we call the leakage, right? Here we assume the parties don't collude. If the parties collude, if party 2 and party 3 work together, yes, they can identify party 1's number, right? This doesn't work for 2 parties only. But this is one of the building blocks. In fact, this is the most simple building block in many of these algorithms, right? And there's much more complicated, secure versions of that where you can prove that there's no collusion possible. Something called homomorphic encryption, where you can encrypt values, do operations on the encrypted values, get the sum back. And but these are the kind of techniques which we're using here, right? So this allows us to calculate the sum, and nobody learns the contribution of the individuals. So you can basically use something like that to calculate edit distance in a secure way. So we have to sum things together. Right, so I think that's probably enough for privacy stuff. Shall we do questions now on this topic, or there's 2 more slides on conclusions? Up to the audience. What do you prefer? Or go to the conclusion, then have questions? No? Okay, let's do the conclusions. Right. Oops. Okay, so just try to summarize many of the things I talked about and kind of an outlook of what maybe some of the research questions are. And again, they come from my computer science background as well. For historical data, which we've seen is these images, having automatic or semi-automatic cleaning and pre-processing techniques is definitely a big challenge, right? So together with the transcription, which again introduces errors and things like that. If you can improve that, so if you have much higher accuracy in digital data, then it will be very useful for linking historical data. Generally, with personal information, there hasn't been much work on these collective techniques, mostly because we don't have that rich environment of different types of entities. If you only have names, addresses, phone numbers, we can't really build large relationships. That could change if you have access to social network data, where you know that 2 people have friends on Facebook and friends on Twitter, or they tweet each other and things like that. I think I mentioned there are no training data about many applications. I'm sure I've convinced you that that's a big challenge. Again, I think the active learning way is the way how we can deal with this, that we include the domain expert, which of course often is interested in achieving high linkage quality rather than trying to do the machine does everything. So combining human intervention. We also, at the moment, I'm not aware of any visualization techniques for these clerical review steps. So basically, instead of just looking at 2 records, are they the same person, we could actually visualize connections and similarities to their parents, their sisters and siblings, etc., and come up with a much richer way of, which would help people do the manual clerical review. So we could highlight in different colors what is the same, what is different, and how these connections are. Being right now is interesting. Linking data from many sources has different challenges. I mean, computationally, do we have to compare every possible pair of records? That explodes exponentially with the number of parties we have. So that's a computational aspect. But then we also have the aspect in privacy-preserving record linkage of collusion, that parties work together to identify information from another party. I mean, a simple question is even what is similar across how do we calculate similarities across 10 parties? If you have 10 John Smith, they're all going to have a similarity of 1, but if you have John, Johnny, Smith, Smithers across 10 parties, the similarity actually goes down if you assume they all have to be, we calculate the similarity across many of parties. We don't have frameworks really, so there's different open source packages, of course commercial software out there, but we don't have a framework which, for example, would allow us to plug in new linkage algorithms and compare them. In other areas of computer science, we have that. So if you learn, like R is a framework where, well, it's not a programming language, but also it's easy to add in new packages. In machine learning, we have Weka, which is an open source Java package, which allows you to do all kind of machine learning. We don't really have such an established framework, open source system, which allows us to do all kind of things. So it's very difficult to make comparative studies. I mentioned this before as well. We don't have test collections. Again, if somebody wants to volunteer data, send me your data. It's very difficult, right? If you have sensitive data, you can't just give it away unless you want to go to prison. Maybe you want to go to prison, I don't know. Truth data is a big challenge. We don't have it in many cases. Again, even if we have some form of truth data, it's potentially not 100% correct. With regard to the privacy aspect, as I mentioned, this is really ongoing research. In order to make them practical, there's not just the algorithms and the techniques and the scalability, but there's even basic things such as how do we measure privacy? It's not something like just accuracy or precision recall. At the moment, there's many different ways of how we measure privacy. There's no established equation which tells me, oh, this privacy is 0.8. Oh, it's better than 0.5, right? Whatever that means, that doesn't exist at the moment. So we've developed disclosure risk measures, something like what's the likelihood that I can re-identify somebody? That's a kind of a measure, right? We haven't looked at advanced classification techniques in privacy-preserving record linkage. So we are just using very simple similarity thresholds. So machine learning in the privacy-preserving framework is an open research. And then the biggest question is this last one. How do we actually measure how good we are in a privacy-preserving framework? If you only have codes, and I can't go back to talk to the people because I'm not allowed to, because that defeats the whole purpose of privacy-preserving linkage, how do I know how good I am? If I look at these hash codes like, oh yeah, that's the same person, that doesn't work, right? So I cannot measure accuracy and I cannot measure completeness. A completely open research question. Any suggestions are welcome. We can, again, some of these we have is using synthetic data, generating hundreds and hundreds of different synthetic data sets based on real data with different characteristics, and that gives us some form of a distribution of linkage quality. And then the last one is a pragmatic challenge, which I've come across several times. If you work with people in different domains, like if you work with historians or these demographers, it's just a different language. People do things differently in different domains, right? It's just getting actually understanding each other. So what does a link mean? What does a match mean? How have you prepared your data and things like that? So, which makes the whole thing very interesting as well. So I think that's the last slide. Actually, just end up with a bit of advertisement. So this is a book which came out of a workshop last year in Amsterdam. Some of you in the audience here wrote that book. You got the chapter in there, right? So this is more like a social science kind of things, but it brings together work from computer scientists and on the social sciences. Very interesting chapters about all aspects of linking populations together. So the book is coming out, it's just got the final proof today actually with a few errors in the tables and things like that. But that should be published in August, so just so that somebody might be interested in that. And that's enough for me. So any questions?
Hi. Is there any kind of tips or rules of thumb to decide whether it's worth attempting record linkage in the first place, depending on how much data you've got? For instance, if you don't have names and addresses, but you do have other characteristics of individuals.
That's a good question. Yeah. So is it worth to do record linkage if you don't have names and addresses? Again, I guess it depends what you want to do and how desperate you are to do things. Like in Australia, as an example, the Australian Bureau of Statistics is not allowed to keep names and addresses over census. There's a law which says you have to destroy all these millions of paper forms, actually shred them and burn them. But they wanted to do longitudinal analysis. So in that case, they were only able to keep things such as postcode, local statistical area, education, religion, age, etc., and try to see how much can they link through that. And there's a few papers which they've published. So I think it's, if you're keen to do things and you want to analyze data, and there's a bit of information you can link, then I guess you can give it a try. I think they were able to keep a sample over a few censuses to validate how good the linkage is, right? Again, if you don't have that, then it's very difficult, right? If you cannot validate. But a good question, yeah.
Thanks.
Must be almost as tired as you are. No, so final chance to get your...
You can talk to me afterwards anyways.
Again, and we will offer our sincere thanks to Peter for
My
a very
pleasure.
informative...
Thanks for coming. Thank you.